So, genetics and hereditary disorders, also an important aspect of clinical science. Definitions we need to remember: gene, a region of DNA that encodes protein; genome, complete set of gene of an organism and the intervening DNA sequence; locus, site of gene on a chromosome; chromosome, self-replicating genetic structure of cells containing the cellular DNA that bears in its nucleotide sequence that linear array of genes. Chromosomes are generally found in pairs. Human beings typically have 23 pairs of chromosomes, 22 autosomes and one sex chromosome. Alleles, alternative form of a gene found at the same locus on a chromosome. A single allele for each locus is inherited separately from each parent. Okay, so it's haploid chromosome and this is diploid chromosome. Haploid is a single set of chromosome, half the full set of genetic material present in the gamete, like egg or sperm, 23. Codon is a sequence of amino acids. Karyotype is the number and appearance of chromosomes in the nucleus. In human, there are 44 autosomes and 2 sex chromosomes. Autosome is an any chromosome other than sex chromosome, 22 pair, except for the sex chromosome, the rest is autosome. So this is like diagrams of autosomal dominant, autosomal recessive, X-linked recessive, and yeah. So we can see here that that for autosomal dominant, it's like affected father and unaffected mother. So white is affected, blue is unaffected. So affected father, and there's 50% chance of the kids having the DNA for autosomal dominant, 25% for autosomal recessive in case both parents are carrier. Okay, and for X-linked recessive, it's usually the both childs are out of 4, 2 will be carrier if one is affected. We'll get to that very soon, but if you remember this very well. Autosomal recessive conditions are metabolic usually. Exceptions are inherited ataxia. So it's all recessives are metabolic. Okay, and autosomal dominant conditions are structural. Exceptions are hyperlipidemia type 2, hypokalemia, periodic paralysis. Rest are structural. So let's see autosomal recessive conditions. The autosomal recessive conditions are often thought to be metabolic, as I said before. So as opposed to autosomal dominant conditions being structural, notable exceptions are, as I said before, mucopolysaccharide, Hunter's disease, X-linked recessive, and G6PD, X-linked recessive. In autosomal recessive inheritance, only homozygotes are affected. Male and female are equally likely to be affected. Does not manifest in every generation, may skip a generation. So here is a classic example of autosomal recessive conditions, like both parents are carrier here, right? If two heterozygotes, as in two heterozygous parents, carrier parents are there, 25% chance of having a homozygote child. Okay, 20% chance of a homozygote child, 50% chance of being a carrier child, and 25% chance of having an unaffected child. Sorry, this is the affected one and this is the normal one. So here it's like white is the normal one, blue is the affected one. So these are two carrier parents, heterozygotes, together is homozygote child, and then carriers and the unaffected child. Okay, the next one is if one so it's if one affected parent, example homozygote for gene, and one unaffected parent, then all will be carriers. This is for autosomal recessive, because both of them are giving off the genes and it's like 50-50, all of them will be carrier. Here when two carriers are there, that's when only this chance of having an affected child. Okay, that's for autosomal recessive. So the important thing is to remember the list that is there for autosomal recessive, this is the big list. Autosomal recessive disorders are often metabolic in structure, nature, and generally more life-threatening compared to autosomal dominant conditions. So it's more life-threatening as well. So results from mutation of 2 copies of the autosomal genes, as we have already studied. The following conditions are autosomal recessive. Most of the C's and G's are recessive. So yeah, C, G, remember that. Albinism, ataxia, telangiectasia, congenital adrenal hyperplasia, cystic fibrosis, cystinuria, familial Mediterranean fever, Fanconi anemia, Friedreich's ataxia, galactosemia, Gaucher, Gilbert syndrome, glycogen storage disease, Gunther disease, hemochromatosis, homocystinuria, limb girdle muscular dystrophy, limb storage disease, maple syrup urine disease. Most of them are like metabolic conditions. Mucopolysaccharide like Hurler's, Niemann-Pick, oculocutaneous albinism, phenylketonuria, sickle cell, TSA, thalassemia, Wilson's disease. So some diseases are there which are very common in life, like in the hospital wards. That's where which these are the ones you need to remember. Also common in the exam, like Wilson's disease, thalassemia, homocystinuria, hemochromatosis, glycogen storage, Gilbert, Friedreich's ataxia, cystinuria, cystic fibrosis, ataxia, all these. Some metabolic conditions such as Hunter's and G6PD are X-linked recessive, while others such as hyperlipidemia type 2 and hypokalemic periodic paralysis are autosomal dominant. Some structural conditions such as ataxia telangiectasia and are autosomal recessive. So structural, but these are like recessive. So for memorizing purpose, they made a small list, a smaller list in fact, so that it's easier to understand, to remember. Uh, these are like albinism, beta thalassemia, cystic fibrosis, deafness, emphysema, Friedreich's ataxia, Gaucher's disease, homocystinuria, hemochromatosis. So autosomal dominant condition. So autosomal dominant, as we have seen before, it's all offspring of an affected person have 50% chance of inheriting the condition. Results from mutation of one copy of the autosomal gene. So the following conditions are autosomal dominant. So here the examples are given at first, like there's a structural problems like achondroplasia, acute intermittent porphyria, um, all hepatic porphyria except congenital erythropoietic porphyria, adult polycystic disease, antithrombin 3 deficiency, Ehlers-Danlos syndrome, familial adenomatous polyposis, familial hypercholesterolemia, hereditary hemorrhagic telangiectasia, hereditary motor and sensory neuropathy, HSMN, including Charcot-Marie-Tooth, hereditary spherocytosis, so a lot of hereditary non-polyposis colorectal carcinoma, Huntington disease, hyperlipidemia type 2, hypokalemia, periodic paralysis, malignant hypothermia, Marfan syndrome, myopathies. All these are there. So the details of autosomal disease. Oh, there are more. Myotonic dystrophy, neurofibromatosis, Noonan syndrome, osteogenesis imperfecta, post-Joger syndrome, retinoblastoma, Romanov syndrome, tuberous sclerosis, Veno-Hippel-Lindau syndrome, von Willebrand disease. So here is an example of autosomal dominant. This is this affected or predisposed father with autosomal dominant faulty gene. It's one gene here, faulty, and this is the unaffected mother. So 50% are affected, getting the gene from the dad, and 50% are not. Okay, so compared to autosomal recessive, which had 25% people having the affected thing. Okay. Okay. So in autosomal dominant disease, both homozygous and heterozygous manifest disease. There is no carrier state, so there is no carrier. Either you have the disease or you don't have it. Both male and female are affected. Only affected individuals can pass on disease. Only affected individual can pass on the disease, and disease is passed on to 50% of the children. Normally appears in every generation, so no skipping of generation. Risk remains the same for each successive pregnancy, and complicating factors can be non-penetrance. Lack of clinical signs and symptoms, so normal phenotype despite abnormal gene, so like 40% autosclerosis. That's dangerous. Spontaneous mutation, new mutation in one of the gametes. 80% of individuals with achondroplasia have unaffected parents. Okay, so this is one of them, and lots of diseases are there, genetical conditions which we really need to know. Okay, the next would be X-linked dominant as well. So if we can just go towards the diagram first, that will be easier for you to understand. X-linked dominant. So this one is like affected mother with the affected eggs and non-carrier father, normal. So here you go, like the girl getting the XD from the mom and X small d from the dad is affected, and then Y from here and XD from here affected. 50-50 for the both boys and girls. Okay, so X-linked dominant is vitamin D rickets, resistant rickets, Alport syndrome, and Rett syndrome. So these are the examples of X-linked dominant. So females have 2 X chromosomes, while male have 1 X and 1 Y chromosome. Okay, we know that. Okay, what's next? If a child has inherited the mutation from X chromosome of one of their parents, they will have the condition. So that's why it's X-linked dominant. So one of them having the X, like the female one usually, a woman with X-linked dominant disorder has a 50% chance of having an affected daughter or son with each pregnancy. The sons of the man with an X-linked dominant disorder will not be affected. So the males have lesser chance uh, if the woman is not having that thing. The sons of the man with X-linked dominant will not be affected since they inherit their only X chromosome from their mother. But his daughters will all inherit the condition. Okay, so this can be a bit tricky at times to understand, but then you have to know there's 50% chance. That's the thing. Like that X chromosome, the male will only get the X chromosome from the mother, right? Because the Y is from the dad, and the Y is from the dad here and here as well. But this D X-linked the dominant faulty gene is coming here. That's why he is affected, and if it's the other one, then he is not affected. That's the thing. 50% chance. Next is X-linked recessive disorder. It's also tricky. X-linked recessive XLR inheritance. Only if males are affected here, and an exception to this is in patients with Turner syndrome who are affected due to only having one X chromosome. XLR disorders are transmitted by heterozygote female carriers, and male-to-male transmission is not seen. Although male can only have unaffected sons and carrier daughters. X-linked recessive, no male-to-male transmission. We will understand that by seeing the diagram. So what's happening here? X-linked recessive. So there is this XX, and there is this XY. So the X is from the male. X-linked recessive, faulty gene from the male. So there's no male-to-male transmission because the male's X is affected. So the sons will not have the X from the male. He will have the X from the mother. So X and Y. So it's always safe, non-carrier. And the ladies are actually genetical carrier because it's getting from one X from the mom and one X from the dad, and the faulty is from the dad. So yeah, that's very easy to understand. The possibility of an affected father having children with a heterozygous carrier is extremely rare. However, in certain Afro-Caribbean communities, G6PD deficiency is relatively common, and homozygous females with clinical manifestations of the enzyme defects are seen. Sons of the carrier have 50% chance of being affected. Daughters have 50 chance of being 50 chance of being affected, of being carriers. Daughters of affected male are carriers 100%. Father is affected, mother is carrier, then all kids have 50% chance. So it's better to just look at the diagrams and understand the thing rather than just playing with the words, which will only make it more confusing for you. Okay, the following conditions are inherited in X-linked recessive fashion. X-linked recessive fashion. Androgen insensitivity syndrome. First one is androgen insensitivity syndrome, then Becker muscular dystrophy, followed by Duchenne muscular dystrophy, Fabry's disease, G6PD deficiency, hemophilia A, B, Hunter's disease, Kalman syndrome, Nielsen syndrome, nephrogenic diabetes insipidus, ocular albinism, retinitis pigmentosa, severe combined immunodeficiency. All these are from X-linked recessive. Wiskott-Aldrich syndrome, combined B and T primary immunodeficiency, and is thought to be caused by mutation by the VASP gene. Features include recurrent bacterial infection, eczema, thrombocytopenia, and low IgG. Chronic granulomatous in more than 70%. Primary immunodeficiency neutrophil disorder has varying patterns of inheritance, with the majority of being an X-linked recessive fashion. Hemophilia is an X-linked recessive and would hence be expected only to occur in males. Patients with Turner syndrome only have one X chromosome. They may develop X-linked recessive conditions. Trinucleotide repeat disorder. Genetic conditions caused by an abnormal number of repeats of a repetitive sequence of 3 nucleotides. These expansions are unstable and may enlarge, which may lead to an earlier age of onset in successive generation. A phenomenon known as anticipation. In most cases, an increase in the severity of symptoms is also noted. The classic definition of an anticipation is earlier onset in successive generation. However, in most cases, an increase in severity of symptoms is also noted. So, earlier onset in the next generations in the disease. Severity of symptoms may also increase. Okay. Examples of this trinucleotide um, repeat disorders are Fragile X, Huntington's CAG, myotonic dystrophy CTG, Friedreich's ataxia GAA is unusual in not demonstrating anticipation. Uh, Fragile X Huntington's includes myotonic dystrophy, Friedreich's ataxia, spinocerebellar ataxia, spinobulbar muscular atrophy, bulbospinal neuropathy, dentatorubral pallidoluysian atrophy. Okay. Anti. Mitochondrial disease. Mitochondrial disease, while most DNA is found in the cell nucleus, a small amount of double-stranded DNA is found in the mitochondria. It encodes protein components of the respiratory chain and some special types of RNA. So, mitochondrial inheritance is the following characteristics. So, what happens in these diseases? Inheritance is only via the maternal line, as the sperm contributes no cytoplasm to the zygote. So, it's only through the maternal line, as these sperms are not contributing to the cytoplasm of the zygote. Okay. All children of affected male will not inherit the disease. All children of affected mother will inherit it, and generally encode rare neurological diseases. Poor genotype-phenotype correlation. Heteroplasmy within a tissue or cell, there can be different mitochondrial populations. Histology muscle biopsy classically shows red ragged fibers due to increased number of mitochondria. So this is for, I think, all mitochondrial diseases. This is for all mitochondrial diseases like red ragged fibers. Okay, so next is examples of mitochondrial disease: Leber's optic atrophy, then Mellus syndrome, mitochondrial encephalomyopathy, lactic acidosis, and stroke-like episodes. So, Mellus syndrome. Mrcp syndrome, myoclonus epilepsy with red ragged fibers. Pearson syndrome, characterized by sideroblastic anemia and exocrine pancreas dysfunction, is usually fatal in infancy. The key patients who survive into adulthood often develop symptoms of Kearns-Sayre syndrome, which is often onset in 20 patients less than 20 years old. External ophthalmoplegia, retinitis pigmentosa, ptosis may be seen. Sensory neural hearing loss, neuropathy, ataxia, and retinitis pigmentosa. Okay. Next is tumor suppressor genes. What are the tumor suppressor genes? Okay, so the tumor suppressor genes, genes which normally control the cell cycle, exhibit a recessive effect, but both copies must be mutated before cancer occurs. So examples are P53, APC, colorectal cancer, neurofibromatosis, RNF1, and RB retinoblastoma. So MYC is an oncogene which encodes a transcription factor. P53 gene is a tumor suppressor gene located on the chromosome 17p. It is the most commonly mutated gene in breast, colon, and lung cancer. P53 is thought to play a crucial role in the cell cycle, preventing entry into the S phase until DNA has been checked and repaired. It may also be a key regulator of apoptosis. Leaf-Fromenyi syndrome is a rare autosomal disorder, dominant disorder. P53 gene mutation, characterized by early onset of variety of cancers, sarcoma and breast cancer. Leaf-Fromenyi syndrome. Okay, next is Down syndrome, a very common one. Trisomy 21 or G is a chromosomal disorder caused by the presence of all or part of an extra 21st chromosome. The condition is characterized by a combination of major and minor differences in structure. Often Down syndrome is associated with some impairment of cognitive ability and physical growth. And with a set of facial characteristics, Down syndrome in the fetus may be identified with amniocentesis during pregnancy or in a baby at birth. Clinical features will be face upslanting palpable fissures, epicanthic folds, brush field spots in iris, protruding tongue and small ears, round face, flat face. A single palmar crease, pronounced sandal gap between big and first toe. Flat occiput, hypotonia, congenital heart defects, 40 to 50%, duodenal atresia, harsh bronchial disease, subfertility, infertility. Cardiac complications, multiple cardiac problems may be present. Endocardial cushion defect. Endocardial cushion defect, 40%, also known as atrioventricular septal canal defect. Ventricular septal defect, 30%. So multiple cardiac problems may be present. Endocardial cushion defect, 40% of the time. VSD, 30%. Second, that means it was ASD, 10%. Etiology 5%. Isolated patent PTA, 5%. This is the main one. Later complications may be subfertility, almost always infertile, due to impaired spermatogenesis. Females are usually subfertile and have an increased incidence of problems with pregnancy and labor, learning difficulties, short stature, repeated respiratory infection, hearing impairment from blue ear, acute lymphoblastic leukemia, hypothyroidism, Alzheimer's, atlantoaxial instability, risk of Down syndrome with increasing maternal age. At 30 years, 1 is to 1000, 35 1 to 350, and so on. The chance of further childbirth chance is approximately 1 in 100 in the person in less than 35-year-old. If the mother is less than 35-year-old, if the trisomy is a risk of the consumption, okay. One way of remembering this is by, okay, start with this and then divide by 3 all the way down. Cytogenetics, non-disjunction, 94% of the case, 1 in 100 if mother is less than 35. Robertsonian translocation, 5%, 10-15% if mother is translocation carrier. Mosaicism, 1%. Okay. Next is Turner syndrome. It's a chromosomal disorder affecting around 1 in 2,500 females. It's caused by either the presence of only one sex chromosome X or a deletion of the short arm of one of the X chromosomes. Turner syndrome is denoted as 45X2 or 45X. So what really happens here? There is increased incidence of autoimmune disease, especially autoimmune thyroiditis and Crohn's disease. And one of the features you see: short stature, shield chest, and widely spaced nipples. A bicuspid, a web-necked, bicuspid aortic valve, coarctation of the aorta, primary amenorrhea, high arched palate, and short fourth metacarpal, multiple pigmented nevi, lymphedema in neonates, especially feet. Okay. Next would be Noonan syndrome. It's often thought as the male Turner syndrome. Noonan syndrome is an autosomal dominant condition. This is a chromosomal disorder. This one. This is an autosomal dominant condition associated with normal karyotype. It's thought to be caused by a defect in the gene on chromosome 12. It's thought to be caused by a defect in the gene on chromosome 12, as well as features like Turner syndrome, web neck, widely spaced nipples, short stature, pectus carinatum, and excavatum. A number of characteristic clinical signs may be present, like low set ears, triangular shaped face, ptosis, cardiac pulmonary valve stenosis, coagulation problem of factor 11 deficiency. So Klinefelter syndrome is hypergonadotrophic hypergonadotrophic. So it's still with karyotype 47XXY. So features are often taller than average, lack of secondary sexual characteristics, small firm testes, hypogonadism, infertile, gynecomastia due to increased risk of incidence of breast cancer, elevated gonadotropin level like LH, FSH are high, so hypergonadotrophic hypogonadism. Diagnosis by chromosomal analysis, karyotyping. So Klinefelter, you know that LH and FSH are raised, and for Kalman, which is coming later, LH and FSH are low normal. Okay, so these are the features you see. Frontal baldness absent, tendency to grow fewer chest hair, breast development, female type pubic hair pattern, small testicular size, long arms and legs, wide hips, narrow shoulders, poor beard growth. All these. If the LH and FSH are inappropriately low normal with a low testosterone concentration, that point was a diagnosis of hypergonadotrophic hypogonadism. Kalman. Okay. If the LH and FSH levels are inappropriately low normal with a low testosterone concentration, that point. Okay. So this one, Kalman is hypogonadotrophic hypogonadism, and for Klinefelter is hypergonadotrophic hypogonadism. Okay, remember that. Okay, Kalman is a recognized cause of delayed puberty secondary to hypogonadotrophic hypogonadism. It's usually inherited as an X-linked recessive trait, and Kalman syndrome is thought to be caused by a failure of GnRH secreting neurons to migrate to the hypothalamus. The clue given in many questions is lack of smell, anosmia in a small boy with delayed puberty. So all these clues you have to find out. Features are delayed puberty, hypogonadism, cryptorchidism, including undescended testes. Sex hormone levels are low. LH, FSH are inappropriately low or normal. Anosmia. Patients are typically of normal and above average height. Cleft lip and visual hearing and defects are seen in some patients. And next is Marfan syndrome, another important disease to remember. So it's an autosomal dominant connective tissue disorder. It's caused by defect in fibrin 1 gene in the chromosome 15. Features would be tall stature with arm span, more than height ratio 1.05, high arched palate, and arachnodactyly spider fingers. Fingers are abnormally long. In some cases, all or few fingers can be bent backwards of 180 degrees. Pectus excavatum, pes planus, scoliosis of more than 20 degrees. Hard dilation of the aortic sinuses, seen in 90%, which may lead to aortic regurgitation, mitral prolapse, aortic dissection. So these ones are the ones that we remember. Dilation of the aortic sinus may lead to aortic regurgitation, mitral prolapse, aortic dissection in Marfan syndrome. Then lungs, repeated pneumothorax, eyes, upward lens dislocation, supratemporal ectopia lentis, blue sclera. All these have to be remembered. That's the main thing. Like these diseases, you have to remember everything that is there, because these keep on coming in the exams. Defect of the fibrin 1 gene, chromosome 15, all these things. Next is Fragile X syndrome. It's a trinucleotide repeat disorder, complete X-linked inheritance. Features in males will be difficulty learning, low, large set ears, long thin face, high arc palate, macroorchidism, large testes, hypotonia. Autism is more common. Mitral valve prolapse. Diagnosis can be made antenatally by chorionic villus sampling or amniocentesis. So analysis of the number of CGG repeats using restriction in nucleus digestion and southern blot analysis. Features in females who have one fragile chromosome and one normal X chromosome, large range from normal to mild. Okay, so you have to remember the features and diagnosis as well. Next is Patau syndrome. Patau syndrome, also known as trisomy 13 and trisomy D, is a chromosomal abnormality, a syndrome in which a patient has an additional chromosome 13 due to the non-disjunction of chromosome during meiosis. Some are caused by Robertsonian translocation. The extra chromosome 13 disrupts the normal course of development, causing the characteristic features of Patau syndrome like all non-disjunction condition. Down syndrome, Edwards syndrome. The risk of this syndrome in the offspring increases with the maternal age at pregnancy, with about 31 years being the average. Patau syndrome affects approximately 1 in 25,000 live births. Infant with Patau demonstrating allobar holoprosencephaly with cyclopia A. Facial features including sloping forehead with proboscis superior to a single central palpebral fissure. B. Close above the fused eyelids and proboscis showing a single nostril. C. Polydactyly showing 6 digits. D. Posterior view of the brain showing indistinct gyri fusion of the hemisphere and occipital encephalocele. E. Transfusion of the aorta and hypoplastic pulmonary trunk. Trisomy 13 or whatever. 13. Karyotype by James A. Banting. Of these embryos that do survive to gestation and subsequent birth, common abnormalities include, of course, mental and motor challenge, polydactyly, microcephaly, low-set ears, whole person cephaly, failure of the forebrain to divide properly, cleft palate, deformed feet known as rocker or bottom feet. Okay, another important one to remember is Prader-Willi syndrome. What is this now? It's an example of genetic imprinting where the phenotype depends on whether the deletion occurs on a gene inherited from the mother or the father. Prader-Willi syndrome if gene derived from father, Angelman syndrome if gene derived from mother. So what happens? Hypotonia during infancy. Dysmorphic features, short stature, hypogonadism and infertility, learning difficulties, childhood obesity, behavioral problems, adolescent acanthosis negligence. So Prader-Willi syndrome is associated with absence of active Prader-Willi gene on the long arm of chromosome 15. This may be due to microdeletion of the paternal 15q1113, a maternal uniparental disomy of chromosome 15. Okay, so remember this. This gene is absent on the chromosome 15, same as Marfan's chromosome. Can be due to microdeletion or maternal disomy. Okay, next is Edwards syndrome. Also another important one. Like none of them are not important, I have to say, because these notes are like very much compressed notes. So this can't be like nobody boarded or stuff. Okay, Edwards syndrome trisomy 18 is a genetic disorder caused by the presence of all or part of an extra 18 chromosome. Extra 18 chromosome. Okay. So that one was Tau was extra 13 chromosome. Okay, it's the second most common autosomal trisomy after Down syndrome that carries to term. It's caused by the presence of 3 as opposed to 2 copies of chromosome 18. The incidence of the syndrome is estimated as 1 in 3,000 live births. Incidence increases as the mother's age increases. The syndrome has a very low rate of survival, resulting from heart, kidney, and other organ disorders. Kidney features would be kidney malformations, structural heart defects at birth, absent radius, intestines protruding outside the body, esophageal apraxia, mental retardation, developmental delays, arthrogryposis, microcephaly accompanied by prominent occiput, cleft lip, cleft palate, upturned nose, clubfoot or rocker bottom feet. Alright, so that's almost close to the end of genetics. Let's have a revision here, like what is there on the list that we need to remove. Trisomy 13, Tau syndrome, trisomy D. 18, Edwards syndrome, trisomy E. Trisomy G is Down syndrome, trisomy 21. So for AML is deletion of 5 and 7. For autosomal dominant polycystic kidney disease, type 1 is 16 gene, type 4 is gene 4. Alpha-1 antitrypsin deficiency, gene 14, lack of protease inhibitor. Alpha thalassemia, gene 16, deficiency of alpha chain in hemoglobin. Alzheimer's, 21, amyloid precursor protein, 14 penicillin, 1 penicillin 2. Most cases are sporadic, 5% are hereditary, autosomal dominant. Autoimmune polyendocrineopathy syndrome, 21, AR. Cystic fibrosis, gene 7, AR. Cystinuria, autosomal recessive, SLC3A1. FAP, autosomal dominant, gene 5. Feminine motor neuron disease, 21, superoxide dismutase deficiency. Friedreich's ataxia, autosomal recessive trinucleotide repeat disorder, 9. Hemochromatosis, autosomal recessive, 6. HL antigen 6. Marfan syndrome, 15, autosomal dominant. Myotonic dystrophy type 2, type 3. NF1 gene 17, NF2 gene 22. Neutron has 7 characters. Remember that. Noonan syndrome gene 12, autosomal dominant. P53 gene 17P, tumor suppressor gene, phenylketonuria 12, recessive. Prader-Willi 15, microdeletion of the paternal 15q1113. Von Hippel-Lindau syndrome 3, autosomal dominant. Burkitt's lymphoma T814 translocation. MYC oncogene is translocated to an immunoglobulin gene. CML, the translocation of T922. BCR-ABL gene codes for a fusion protein which has tyrosine kinase activity in excess of normal Philadelphia chromosome. Mantle cell lymphoma 1114, deregulation of the cyclin D1 gene. Promyelocytic leukemia T1517, fusion of PML and RAR alpha genes. So that's it for now.